Well, maybe. I can open that up. All right, so got, what was it, 12 square feet of material to make a sphere and a tetrahedron. Right. And you're trying to maximize and minimize the volume. All right, so one of the things that we need to know would be the volume of each of those two things, right? Well, sphere, oops, I was going to write. Four-thirds pi r cubed. Yeah.
We're supposed to be seeing something.
Oh, yeah, you should be seeing something. Sorry, my bad. Thank you. I could have done all day if you hadn't said something. I would have just kept writing. All right. We also need the volume for a tetrahedron, which you probably needed to look up. Yeah.
Yep.
What did you get? What was it again? Sorry. That? Something like that?
I had over 12 as well. A cubed times root 2
over 12. Okay, cool. All right. Excellent. I don't remember what it is either. I would have to look it up. So that's fine. That's what Google's for, right? Okay. All right. So we know that the total, and then we also know surface area for a sphere would be 4 pi r squared. And then we also have surface area for a tetrahedron. Let's see. That one should be root 3 over 4 times root 3a squared. The area one I know, because you should have 4 equilateral triangular faces. Well, area of an equilateral triangle is square root 3 over 4 times the side length squared. And there should be 4 sides. 4 faces. I think that's square root 3 over 3a squared. But equilateral triangle we can do. I mean, that one's not too bad. We should be able to do that. If this is A and you drop it down your perpendicular, you get A over 2. So the length of that side is root 3A over 2. 1/2 base times height gives you root 3 over 4A squared. And then you got 4 faces for a tetrahedron. So it should be root 3A squared. That one I can do. I remember that one because I can derive it. Volume. I could have done the volume too. It just would have taken a little bit longer. You would have to do, remember for a pyramid, your formula for volume is 1/3 the area of the base times the height. So the area of the base in this case would be root 3 over 4a squared. And then you just need to figure out the height of the pyramid in terms of the height of the tetrahedron in terms of the side length, which is not too bad of a problem to do. I know geometry. All right, anyway. So we know that, pardon me, the total volume then will be 4/3 pi r cubed plus root 2 over 12a cubed. Right? Okay. And we know that the total surface area must be 12. So those are 2 pieces of information that we know. So you're trying to find the maximum and the minimum volume of the total volumes together of the sphere and the tetrahedron. So the volume of that particular function. All right, notice this has 2 variables in it, so we're going to use this equation to solve for one of the variables in terms of the other. Yeah. Okay. So solve for a squared, say, in terms of r squared. Thank you. Pardon me. So you get a squared would be what? 12 minus 4 pi r squared over root 3. And we can plug that into the volume formula then, so you get a volume in terms of the radius. Oops. Oops. Squared over root 3, and this should be to the, looks like to the 3/2 power. Okay. Now I need a function to find the maximum of that function, right? An absolute maximum problem, right? So remember that back to Calc 1, how do you find absolute maximums? What do you do? Yeah, so I need to take a derivative, right? What do we do with the derivative? Yeah, set it equal to 0 and solve. So that's where the numerical method's going to come in, right? You take the derivative of this thing and then figure out where that derivative is going to be 0, right? So that finds a critical number, but if we're doing absolute max min, not only do we need critical numbers, what else do we need? Yeah, we need the endpoints, right? Because remember, for absolute max min, we got to check critical numbers in the interval and the endpoints and see which one gives us the biggest, which one gives us the smallest, right? So you'll take the derivative of this, use R or Excel, either or, doesn't matter, to figure out what the critical number is. I mean, you'll differentiate it, but right? You take the derivative of it, but that's not too bad. You know how to differentiate. It's a requirement for getting into classes. At some point, you should have differentiated something. Okay. All right. So take the derivative, set it equal to 0. What do we know about endpoints? Well, we got to think about the physical constraints of the problems as far as endpoints. We either don't create a sphere at all, or we don't create a tetrahedron at all. Everything goes to everything, all sphere. Everything goes to all tetrahedron, or in somewhere in between, right? If it's all tetrahedron and no sphere, what does that tell you the R value is? 0, right? It'll tell you the R value is 0 if we don't use the sphere at all and put everything into the tetrahedron, right? So that would be, you would use 0 for one of your endpoints, and then that would just give you whatever the volume of the tetrahedron is for putting everything into the tetrahedron. Go the other way, if it's all sphere and no tetrahedron, that means the side length has to be what for the tetrahedron? 0, right? So if I set the side length equal to 0, you can solve for the R here. I believe gives you square root of 3 over pi. The numerator there would have to be 0. So you'll get the critical number using your numerical methods. Take the derivative, set it equal to 0. Use probably secant method because you already took one derivative. You probably don't want to do another one to use Newton's. But secant method is probably a little bit easier. One thing you would not want to use on the secant method is 0 for one of your endpoints because it turns out to make the derivative 0 as well. So that was and then once you figure out your critical number and the endpoints, plug all 3 into your volume. The biggest is the max, the smallest is the min. So not unlike one of the other problems where you had to solve for one of the variables in terms of the other to get a function of a single variable, right? There's another problem you had to do that in. 4? Okay. 4? No, 4. 4 was the interest problem, wasn't it? 3, maybe. I don't remember. Whatever number it was. 4 was the one with the interest, right? Yeah. Okay. So that one was, goodness gracious. Pardon me. But there was another one where you had to solve for one variable in terms of the other. You had a height or something along those lines, right? So you get rid of it. I can't remember which one number it was. So same idea, so that you get a function of a single variable. The one extra step for this one particular problem is I had to take the derivative and find to set that derivative equal to 0 to find a critical number. I don't know, a little more complicated than the other ones, I agree. It's also like it's a homework problem. Right? Not a test problem, it's a homework problem. That's why it was a homework problem, to get you to think through it. The idea okay though? And I'll post an answer key too, so you can see the answers as well. So the process okay? Other questions? Everyone's okay? Number 4 is also difficult. Number 4 is a little bit difficult? Okay. So, pardon me. One of the problems with number 4 is because the root was tiny. So, give you this formula. Nope, that's backward. Right, that was the formula that we were given. You borrowed $160,000 and made $1,000 monthly payments for 20 years. The N represents total number of payments, so I do need to change that to 240. 12 times the 20. And then I want to figure out what the I is in this case. So same premise here, I would subtract the set it equal to 0. Notice you probably don't want to use Newton's method. Why don't you want to use Newton's method here? Yeah, I have to take derivative of that nasty thing, right? I don't really want to do that, okay? So that's probably why I don't want to use Newton's method here, because now I have to take a derivative of something that's not pleasant to take the derivative of. It's horrendous, but still not fun. So problem with this one is that if you don't use numbers that are close to where the root is, you're probably going to go find the one that's negative, which makes no sense, right? There is a root that's negative, but negative interest rate doesn't make any sense. So it turns out that this root's pretty tiny. So you need to start with pretty tiny numbers. I would have probably started with something like 1,000 and 2,000 or something like that. It's just a matter of playing around with the tiny numbers to get at that. Interest rates are typically in decimals, so using smaller decimals is probably easier. And that's a monthly interest rate rather than an yearly interest rate. So if you're thinking of an interest rate being at even 4%, if I do that for 12 months, it would be like 0.003. When you convert it to a decimal for a monthly interest rate. So the rates are tiny. So that's what you have to use tinier numbers, and you should find out what's the correct answer at that point. I'm assuming the setup wasn't the problem. It was trying to get R to get out the right value. Yeah. Pardon me. It was just a matter of finding the right. Was a lot of people getting the negative value when they ran the first time?
I thought we were supposed to do it by hand, so I have 2 pages worth of steps.
Oh my goodness. No. No, don't do that with my hand. That's nasty.
I am lucky I have a really fancy calculator, so it was just a matter of like continually setting the variable to the new value and plugging it back.
Oh, sure. No, I understand that. That's gross. Yeah, don't do that.
30 minutes?
Yeah, I'm guessing it would take
I did
about.
also run into a problem where I misassigned the variable partway through, so I had to go back and redo
Oh,
it.
jeez.
So that led to part of the 30 minutes.
That's nasty. Yeah.
It's already took me long.
Yeah, if you put 0 in here, it's going to cause an issue because it's got a vertical asymptote of 0. So try to use 0 as one of your endpoints would be a bad one to try to use. That's not a number. Same thing will happen if you're doing things with square roots and put something in negative. You pick a value that's too big, it'll be not a number as well. So the setup wasn't the problem; it was trying to get it to converge is the issue. Yeah. So it's another one of those to think through what you're looking for, right? If you're actually looking for an honest to goodness interest rate, it's as a decimal, it's going to be small, and then if it's monthly interest rate, it's going to be divided by 12, so it's even smaller. So it's just a matter of trying to figure out what some limits are to start with. Good news is, again, that you're not using bisection method here, so you're not looking for trying to bound where it crosses. You just need to start with 2 things that are close. So secant method, and then it should converge for you. Just have to play with it a little bit to get it to work. But it is a good example of another one of those that goes, if you pick bad numbers to start with, it goes and finds another root that you don't want. Because negative interest rates are not what you're looking for. I mean, unless you're the person that you're going to invest the money for people. If somebody's going to give you money to invest, you're going to give them a negative interest rate, that's fine because they can pay you to handle their money. That's what a negative interest rate would be, right? You give somebody else money and say, hey, you save this for me. Sure, I'll charge you this much to do it. And then not give you anything back. Something bad to you. Other questions? Sounds like you were challenged.
Yep.
Good. All right. Again, it's a homework problem. Remember that homework is not worth as much as other other things as far as doing the major assignments and the quiz as far as, right? The homework was 20% overall, and this is one problem out of however many. Hey, Justin. How are you?
I'm all
All right. So we'll have more about homework assignments as we go along. As a matter of fact, I'm going to give you one today for next week. So don't fret too much about one particular homework problem, right? The whole problem of this was to get you to start thinking through things so that when doing major assessment time problems, when you're going home and working on those things, will be a little bit more, you'll have ideas of how to attack them. That's the whole point. All right. Any other questions before we do some new stuff today? Okay. And again, if you've got more questions about the individual problems, please feel free to come by and see me. I'm happy to go over things. Any questions? All right. So last time we talked about working with Horner's algorithm, coding that up, and then how we can get the different derivatives out of it. So just to remind again, let's do a quick one. So if you had f of x is equal to, let's say, 2x to the fourth minus 3x squared, let's do 3x cubed, plus 4x squared minus x plus 2. And I ask you to find all the non-trivial derivatives. I can spell derivatives, that would be helpful. At, let's do x equal to 3. So remember again, we can use Horner's algorithm to figure out the function value at 3. And then we can keep going and do repeated applications of Horner's algorithm to get us those coefficients of recentering the polynomial at 3. I'm going to go through it here in a second. And then recognizing that we have an expression for the Taylor series is how we can get those those derivatives out of it. So we'll just do this one by hand since we're sitting here anyway. So go through Horner's algorithm by hand here. We'll put our coefficients for our polynomial up at the top. If one of the powers of x is missing, then I'll want to put a 0 in if I'm doing this with Horner's algorithm, right? Make sure I put a 0 coefficient in there for that. What's the process again? What did we do with the 2? We bring it down, and then we multiply, and then we add, and then we multiply, add, multiply, add. I made a big number. Multiply, add. That process okay, I hope. What does the 116 represent? Yes, the remainder this is actually f of 3, right? Okay. So when I ask for the non-trivial derivatives, of course, at most I need to take how many derivatives of this polynomial before it gets to 0. Yeah, so I think the fifth derivative will hit 0, right? Because when I do the fourth derivative of x to the fourth, I'll end up with a constant. When I say the fifth derivative will be 0. So when I ask a question like this, I mean, take as many derivatives as there was for the degree, because the next one will be a 0, correct? All right. So we'll do this a few more times to get down where we need to. Do it again. So remember to do it again. We'll lop off this one. We don't use the 116 because that's the remainder. Do it again. Bring down the 2. Multiply. Add. Multiply. I should have put more negatives in here so these numbers were smaller. And add. did it quickly, but the process okay? I think you all seem to be okay with the process. I'll go ahead and do it fast. If not, throw something at me. Holler at me. All right. So we'll come back to what the derivatives are here in a second, but the 158 we'll use. We'll do it again. Lop off the 158. We don't need the 158 anymore. Bring down the 2. Multiply, add, multiply, add. Again, don't need the 85. Bring down the 2. Multiply, add. Ooh, hey, that was ugly. And then, of course, that last 2, we know we're essentially done, right? Because the next one, we just bring down the 2, we would be done. All right, so this is how we know to quit. We get down to where we only have this one part left. So this is how we use these. Remember we talked about this last time, how we recenter the polynomial from being at x equal to 0 to be x at equal to some other center, right? In this case, we've plugged in 3 every single time. So we can rewrite the polynomial as 2 times x minus 3 to the 4th plus 21 times x minus 3 cubed, 85 times x minus 3 squared, 116 times x minus 3. Nope, not 116, 158, sorry. Plus 116. So the numbers that are left over here are your coefficients on x minus 7 or x minus 3 to whatever power it is, right? So this was the last one, so that's the highest degree term that we had left. So we have the 2x minus 3 to the 4th. It makes sense that that number should be the same because remember we had a 2x to the 4th term at the beginning, right? That was our leading coefficient, was a 2. Well, the only place that you can get an x to the 4th out of this simplification is if I multiply out x minus 3 to the 4th. So that one better be a 2, right? And then we get the rest of the coefficients going backward through our synthetic division process, or Horner's algorithm process. Yeah. Should it be minus 158? Oh, and so it's a positive 158, right? So that's why it's plus. But again, like I said, this 2 should not have been a surprise. Because if you multiply all of this stuff out of here, the only place you get an x to the 4th is here. And the polynomials have to be equal. Your question? So remember the 2 is the coefficient on the x to the 4th, right? Here. So that's where that 2 is coming from. The 3 is what we divided by. The 3 is what's going in here for each of the centers here. Okay. So again, remember the whole reason why this works is because we're doing that synthetic division. We're dividing by the x minus 3, figuring out the remainder, pulling off the remainder, dividing the x minus 3 through it, canceling things out, and doing it again. Okay, so those remainders are what we're pulling off to get these values. Okay. All right, so this is the process for going and recentering the polynomial at a different point. Now, we can also use this to figure out what the derivatives have to be. This also looks like the Taylor series, centered at x equal to 3, right? Remember when we do a Taylor series, when we do our Taylor series at x equal to a, centered at x equal to a, the coefficients or the format of it looks like that. The coefficients on your x minus a to the n term are the nth derivatives divided by the n factorial piece, right? So this looks like a Taylor series. In fact, it is the Taylor series for the polynomial that we were given, just recentered at 3 instead of at 0. It is the Taylor series for that polynomial, we just shifted it. If this is the Taylor series for the polynomial, remember, if a function has a Taylor series, expansion at a point, then, pardon me, it's unique. You can only have one Taylor series expansion centered at a particular point. It has to be unique. Okay? So what that tells us is that, for example, the first derivative of the polynomial at 3 has to be 158, because this first derivative at 3 has to be 158. That has to be the Taylor coefficient. Right? What does 85 have to equal? So the f double prime of 3 over the 2, right? Because of the n factorial, right? So our 85 here, oops. So the 85 has to be the second derivative at 3 over 2 factorial. So the second derivative at 3 has to be 170 in this case, multiplying both sides by 2. Okay. What does the 21 represent? The third derivative at 3 divided by 6. Yeah, the 3 factorial, right? So the third derivative at 3 has to be, what, 126? Then finally, what does the 2 represent? Yeah, fourth derivative divided by 4 factorial. Good. So our 2 is the fourth derivative evaluated at 3 over 4 factorial. 4 factorial is 24, so the fourth derivative at 3 is 48. First Tuesday of the month. And then that's it, right? Every other derivative will be 0 past that point. So we can use Horner's algorithm here to help us find these derivatives of the polynomial at a particular point, running through it. And it looks like something that you could program pretty quickly. Just have to go through it. You already have a function that we wrote for R last time that'll do Horner's algorithm, right? So basically you need to send your polynomial through Horner's algorithm, pick off the last term, right? Then drop it off, send the polynomial back through Horner's algorithm again, and just keep doing that process, looping through until you run out of coefficients. So it sounds like a good R program to write, and that might be something that I'm going to ask you to do for homework. Okay. You already have Horner's algorithm to write, so you just need to figure out how to loop things through and collect. That's going to be the idea of what you need to do for the program. You already have Horner's algorithm, so that's not a problem. So it's just a matter of getting the looping structure to work and pick out the pieces that you want. Any questions on how we did this at all? Is it okay? Everybody's thrilled. Apparently I took the wind out of everybody's sails by going through that problem at the beginning of class. All right, well, we'll continue on. All right, so the stuff that we did with Horner's algorithm, representing with the nested multiplications and those kind of ideas, we did in this. It was the first section of your text. The second section of your text goes through a discussion of Taylor series. We've already talked about some ideas with Taylor series that we need. We've talked about how we represent functions as Taylor series. We talked about Taylor's form of the remainder when we went through showing that Newton's method converged quadratically. Remember we had that little form of the Taylor's remainder. They do a little bit more in-depth discussion in section 2. I'm not going to go through that right now. We will pick up pieces of what we might need for Taylor's theorem as we do it this semester. I'm not going to spend a long-winded time talking about developing Taylor series and proving that a function is actually equal to its Taylor series, or showing that a function doesn't have a Taylor series, although I will do one example of that here in a second because I've mentioned it a couple of times. There's a lot of stuff in one small section that we could spend weeks on, and I'm not going to spend weeks on it. So we want to talk about solving problems. Okay? So just keep in mind that we might come back to section 1.2 stuff later on as we need to gather some Taylor series stuff as we need it. I will mention that there are functions, again, that do not have Taylor series expansions at particular points. So, for example, if you say you have something like even f of x equals square root of x, this does not have Maclaurin series expansion. Remember, Maclaurin series is Taylor series centered at 0. So f of x equals square root of x does not have a Maclaurin series expansion. You cannot find a Maclaurin series for root x. We cannot expand that at 0. So remember, again, how we find Taylor series. The first thing we start doing is taking derivatives, right? What is the derivative of square root of x? Yeah, 1/2 x to the negative 1/2. And then we would keep going and take a bunch of derivatives, right? That's the first step you do when you try to find a Taylor series expansion or a Maclaurin series expansion. Take a bunch of derivatives. What's the next thing that you do? Plug in the center, right? Because I needed the derivatives evaluated at the center. For Maclaurin series, the center is 0. Can I put 0 in there? No. Okay? That's why it doesn't have a Maclaurin series expansion. I cannot plug in a derivative. I cannot plug in 0 into the derivative. Nothing special necessarily about a half. The x to the 1/2, I mean. You could have done x to the third. You could have done x to the 7/5. Anything where you have powers and you start differentiating the power and it's not an integer, you're going to get a negative exponent eventually. Right? If the exponent is not an integer to start with, take enough derivatives, the exponent will become negative, and you no longer will be able to plug in the 0 in for that. Okay? So you won't have Maclaurin series for anything that's x to a power that's not an integer power, a positive integer power, I should say. You can also have a function that doesn't have a Maclaurin series expansion that actually you can differentiate infinitely without any issues. They're weird functions. If you have the following, take the piecewise defined function that's e to the minus 1 over x squared on the positive side and 0 on the negative side. Notice that I can plug 0 into this function because it goes in here. Also notice this function is continuous. As x gets really, really small, x squared gets really, really small, even smaller, right? 1 over x squared then gets really, really big, and it's going in the negative direction. E to a big negative number is really, really small, okay? So as x approaches 0, in this case from the right, but as x approaches 0, this goes to 0. This goes to 0. Okay? So it's continuous. There's no issues with continuity. The graph of this function is constant to the x-axis and then goes up this way. Okay. It's really, really flat here, and then goes up, and then as x gets big, it'll get small again. As x gets big, this gets really, really small, right? And you're doing x to negative small values, it'll end up going to 1, something like that. Because the exponent goes to 0, right? So you'll have a horizontal asymptote at 1. What's interesting here is that this flattens out so much that the nth derivative at 0 is 0 for all n. I'm not going to show that, but that 1 over x squared in the exponent and then doing the negative of it makes all derivatives of all orders at 0 for this function to be 0. So what would your Taylor series end up being all the time? If all your derivatives are all 0, then the Taylor series would just be 0, right? This function is certainly not the 0 function. Okay. So it's not equal to its Taylor series. Except at 0, which is not interesting. So here's a function that's defined everywhere. We can differentiate it for all orders. We can take every derivative that we want, and it still doesn't have a Taylor series. It seems like an odd, a strange function, right? But it's not all that strange. It just flattens out so much at 0 that the derivatives are all 0. So I just wanted to give you a couple of examples. When we talk about Taylor series being the things that we want to use to approximate functions with polynomials, but with some of these functions, either we have to be clever and do it somewhere else, because this one we can't do it at 0 because the derivatives aren't defined, or we just don't have any hope of being able to do it at a particular point. Okay. That's mainly what I wanted to mention about Taylor series from the weird cases. We're not going to run into many weird cases, so we don't have to worry too much about that. But I wanted to give you some examples of things that just don't work. Because, again, Taylor series are important for us to be able to get our hands on things that are transcendental. Sine function, cosine function, exponential function. Those are things that we can't do arithmetically. We can't do with algebraic operations, right? So we need polynomial ways to approximate them so that the computer will work. All right. We're going to switch gears a little bit when we get to section 1.3 here. And we're going to talk about, pardon me, the way the machine, the computer, the calculator, represents numbers. So I'm assuming that you're familiar with scientific notation. So generally speaking, when you have something in scientific notation, you've got some part, I'll call it Q, and then 10 to some power, I'll call it P for lack of a better word, letter, whatever. What has to be true about the Q when we write something in scientific notation? Yeah, it's between 1 and 10, right? So when we write something in scientific notation, our Q here is going to be in between. It definitely could be 1. It could actually equal 1, right? But it has to be less than 10. Because if it turns out to be bigger than 10, then you just bump the exponent up on the 10, right? Now, we're going to change this over to a different way of expressing something in what looks like scientific notation. But we're going to change it to a different base. We're going to change everything, for our purposes, we're going to change everything to base 2. Because again, we're dealing with computers. Computers only know how to turn switches on and off. Well, if we represent off with 0 and on with 1, we can represent numbers in base 2 with switches. Okay. So we're going to talk about how we convert over to base 2. Now, what's interesting about base 2 is that if we have this part here, and we think about it as a decimal, I don't want this to be 0 point something. Oh, I will have something 0 point something. But notice that if I write this in what would be scientific notation in binary, if I think about doing is 2 to a power on the other side, well, I can only have zeros or ones for the other pieces, right? So if you think about it in the same idea for binary, this number is always going to have to start with a 1, right? The reason why we say less than or equal to 1, excuse me, greater than or equal to 1 and less than 10 is because we don't want a 0 on that first part, right? And we don't want something bigger than 10 because if it's bigger than 10, then we just move the decimal place over, right? Well, for binary, I wouldn't want a 0 there for the same idea, right? You don't want a 0 here in scientific notation. Well, then I have a 1 there. It can't be a 2 because 2 is not an allowable digit. The only digits you have in binary are 0 and 1. So when you write something in scientific notation for binary, you're guaranteed that that first number has to be a 1 in scientific notation. Whatever's to the left of the, we don't call it a decimal point. I'll call it a binary point for right now. Decimal point means base 10, right? Decimal point, right? If you talk about doing it in other bases, it's usually called a radix point. But we'll call it a binary point because it's for binary. Whatever is on that left side of the binary point for binary in scientific notation has to be a 1. Well, if it has to be a 1, is there any point in storing it in the computer? If you know it absolutely has to be a 1, there's no point in storing it because you know it has to be a 1. Okay? So that's one of the things that computers will do when you're storing a number that's written in this normalized notation that we're going to talk about. When you're doing it in binary, I never worry about storing that first 1 because it has to be a 1, unless the number is 0. Right? If the number is 0, then we know it's a 0. But otherwise, that first place that's right next to the binary point has to be a 1. So there's absolutely no point in storing it. Okay? All right. So we'll talk about that storage here in a second, but let's remind how we convert things to other bases. So if we'll do this generally, and the only thing we're going to convert is to base 2. Let's start with a whole number. So let's say you started with 587, just for lack of a better number to start with. And I want to convert it to another base. Well, let's think about what this means in base 10. In base 10, this means that you've got 7 1s, 8 10s, and 5 100s, right? And this here is where the base is, right? Each place represents a power of the base, right? The 1's place is 10 to the 0. This place is 10 to the first. This place is 10 to the second, and so on across, right? Well, if the bases now don't necessarily, if the places now don't represent the powers of 10, but powers of some other number, what we're interested in is rewriting this 587 as some zeros place, right? I'll just call it A0 to start with, plus A1 times B, where B is my base that I'm trying to convert to, and then plus A2 times B squared, A3 times B cubed, and so on until I need to stop, or I can stop. I want to write it where I know that this is the zeros place digit, this is the B to the first place digit, this is the B squared place digit, B cubed place digit, and so on down the line. Okay? That's the idea by changing this to a different base. Okay? So instead of, again, here each place is representing a power of 10. We want to convert it so that each place represents a power of some base. Okay? That makes sense? All right. So let's talk about the process involved in doing this, and then we're going to do the same thing with on the other side of the decimal point. And then we'll do a little bit of playing in Excel and perhaps R as well. So, all right, if these two things are supposed to be equal, if I divide both sides by B, whatever B happens to be, it would still have to be equal, right? Right? Okay. If I look at just this part right here, some of you may have already done this, so you might be bored with what I'm saying. If I look at just this part and divide that by B, what would the remainder be for that part that is underlined in red? If I divide it by B, what would the remainder be when you divide it by B? Okay, let's think about it. Let's look at this here. Can I pull out a B? Yeah. So if I divide it by B, it'll just evenly go in, won't it? So the remainder will be, it'll be 0 for this part, right? There won't be any remainder when I divide it by B, right? Just like for this part here. If I look at this part right here, this is 580. If I divide it by 10, is there any remainder? No. Okay. So same idea here, right? So this part right here has, well, let me change back to black. Has 0 remainder when divided by B. Oops. Right? So if you divide the entire right-hand side by B, what does the remainder have to be? The A0 part, right? The remainder part is just the A0, because I'm looking at just remainders, the whole number part, right? You're right, as a fraction, it would just be A0 over B, that would be the fractional part, right? But the remainder is A0. So if I divide the right-hand side by B, the remainder we get is A0, right? Well, if everything is equal here, if this is the remainder when I divide by B on this side, it better be equal to when we divide by B, the remainder when we divide by B on this side, right? So that's how we're going to find that first place, that first B's place, if you will, right? We're going to divide both sides by whatever the B is. The remainder gives us that digit that's closest to the radix point. I will slip and call it decimal point, but again, decimal refers to base 10. I think we're all okay with what we mean by that dot, okay? But this A naught, that first remainder that we get will be the one that's closest to that point, okay? Now, how do we find the A1? Well, if I subtract the remainder from both sides, I now have a multiple of B on both sides that I can divide out, right? So I'm going to write it in, I'm not going to go through this in symbols all the way through. If we subtract off the remainder and then divide by the B, because I know if I subtract out the remainder, I get something that's evenly divisible by B, right? Okay. Over here, subtract off the remainder, which was A naught, and divide by B. Oops, that's just A2B. Notice that we get a factor of B that cancels all the way on the right-hand side, don't we? So how do you think we're going to figure out what A1 is? And so if we subtract the remainder of line by B, that gives us this expression. Now that we have a number on the left-hand side, how do you think we're going to figure out what A1 is? Yeah, do the remainder again, right? Do the exact same thing we did in the previous part, right? Divide both sides by B. The remainder on the right-hand side is A1, so the remainder on the left-hand side has to be what A1 is. Once we figure out that one, what do you think we're going to do? Subtract, divide, do it again, right? Keep doing this process over and over again. This is how you convert from one number to another, or one base to another, okay? So this is pretty, actually straightforward to program it into Excel. You zoom in here so that you can actually see what I'm typing in Excel. All right. So the first thing I want to type in A1 is going to be the base that we're going to convert to. Okay. So let's say we want to convert that 587 that we were just working with to base 6. I'm just making that up. Okay. Right. So I'll put a 6 up here in the upper left-hand corner. I'm not going to touch that 6 unless I want to change it to converting it to a different base. Okay. And again, we're trying to convert 587. So 587 is the number we'll start with, so I'll type it here. If I want to convert a different number, we can convert that different number. Just retype that in there, and it'll just change all the computations later on. So we'll base everything on grabbing this for our base and grabbing this for what we're changing. Okay. When we grab this for our base, we'll use absolute cell reference because I'm not going to want that to change as I copy down because I want to use the same base every single time. When I refer to this 587, of course, I'm going to want cell references because I'm going to change it as I move. All right. So when we talk about doing remainders, there's a couple of ways that we can do this. One's, if you know what the function is, I'm going to mention it here in a minute. You know what the function is, pretty easy. But if you want remainder, remember the remainder refers to what the decimal part is, essentially, right? So you can figure out what the quotient is. To figure out what the whole number quotient part is, let me just type that in. I'm going to actually come back and make this simpler, but I just want to show you real quick. There's a couple of different ways to get the integer part of a number that we want. We can use the floor function. The floor function just means that you always round down, which works just fine. For positive numbers, for negative numbers, the floor function is a little weird because you round down to the integer that's below it. So if you wanted to do the floor of negative 2.5, you actually get negative 3 as it goes down. Instead of you really want the negative 2 part if you're thinking about the integer piece. So the integer part of, I'll just grab this part, divided by the base, and then again we'll change that to absolute cell reference. This will give you the quotient. I'm dividing the number by the base here. That'll give you the quotient. Gives me 97. To get the remainder, you would take what you started with and subtract off the quotient times what you divided by. So it would be this absolute cell reference times the quotient that we just computed. Remember that 97 is referring to how many times 6 went into it evenly, right? 97 times 6 would be the biggest whole number, less than 587. That isn't a multiple, or that is a multiple. It's the biggest multiple of 6. That's less than 587. This number, of course, is the remainder. It should always be between 0 and 1 less than the number. We actually get a remainder of 5 here, right? Agree with that? Okay. All right, so remember that this number right here represents how many times that 6 didn't even bother going into the number, right? It's the remainder when we divide it by 6, right? This is now what's left over. This is what you get if I take 587, subtract the remainder, and divide by 6. That's what this piece is, right? So the integer command is just taking off that integer part. This is now the part we want to divide by b again, right? Divide by 6 again. This part over here is the remainder that we computed, so I can just take this, highlight it, and copy. Oops, what did I do? Oh, I need to copy this over, sorry, because it was referring back to that. I want to grab that number. So I'm going to grab that 97 and put it here so that when I copy down, now I get 97 divided by 6. gives me 16 with a remainder of 1. And now I should be able to copy this down a couple more times. Eventually, everything's going to go to 0. So we'll take the 16 divided by 6. We get, goes in 2 times with a remainder of 4. 2, 6 doesn't go in at all with a remainder of 2, and then we're done, right? Okay. So again, the way we computed this was our successive remainders. This is our first remainder, this is the second, this is the third, this is the fourth. And remember, this starts off closest to that radix point, right? It's the one next to the decimal point, right? So if we go back and write this number now, yep, I will just a sec here. Okay, so going through all of this, then our 587 is going to be 2415, and then to say that this is base 6, we'll put it as a little subscript. So we'll have 587. When we don't write a base, we assume it's base 10. 2415. Notice I'm writing going up here, that way. Okay. All right. C2, you said? C2 is just copied from C1. It's just copied down from C1.
What did we do for B2?
B2, I just copied C1 over. It's just because I'm copying down that quotient is the next thing we're going to divide by. D1. Oops. That is that one. So that's figuring out what the remainder is. So it's taking the number you started with and subtracting off the quotient times what you divided by. So that'll give you the remainder.
Can you explain what the dollar signs mean again for the
So the dollar sign is what's referred to as an absolute cell reference. When I copy that cell, every single time I want to make sure I'm dividing by 6. So I don't want that to change when I copy. So when I put a dollar sign next to the column, no matter where I copy that formula, the column will never change. When I put the dollar sign next to the row, it won't change the row. So since I put it on both of them, it'll just fix on that cell and never change it. Oh, sure. So C1 is what's computing our quotient for us. So we use the integer command. We could use the floor command. In this case, it would give us the same answer. We're not going to have anything in here that's negative, so it would give us the same answer. We could use the floor command as well if you're more comfortable with using floor rather than int. It makes zero difference to me because we're not doing anything with negatives. But we do want to pick, we don't want the decimal part. The decimal part was representing the remainder. I don't want the decimal part, I want the quotient part. That's why I'm using the integer command. I just want the quotient part. Because again, the quotient part is what we're going to divide into in the next step. Is that okay? And again, if I want to convert this to a different base now, I can change, since we've got it set up, everything set up, I can just type in the new base. So if I wanted to convert it to base 4, I just replace the 6 with a 4, it'll change it. Okay. If you want to change it to base 8, ta-da, changes it to base 8. Base 8, base 2, base 8, base 16 are used a lot in computer science because they're powers of 2, octal and hexadecimal. Base 16, you have to use letters to represent 10 through 15 because you need a single entry into a digit. We're going to be interested in binary more than anything because we're interested in talking about how the computer stores the numbers. This okay for this part? Yeah.
Where'd you get the 2415 that you wrote down for the base 6?
So again, This is representing the part that's right next to the radix point. So we're just going in reverse order. So
Oh, okay.
5, 1, 2, yeah, 1, 5, 1, 4, 2. We're writing it that way. Let's say you have a question. You should be able to just copy that cell down. Where the 5 is, just copy it down. So then just copy your other cells down there too. They should match. Do the one where the 16 is as well. Oh, because you typed it. Just copy this. You're welcome. Okay, so we want to just take this and copy down here. So we want to type in that cell right there, the E2, and type in equals. And then you should be able to copy those two cells down to the next line. I'll go back to that. There you go. Grab a little cell and make columns or take all three. Yep. Okay. So again, what we're going to be more interested in anything is the binary. So a lot of times you'll have a 2 up here in the upper left-hand corner. Notice that I'm not done in binary, right? This is done when we start seeing zeros everywhere. So I would want to copy this down farther. Does that make sense? Okay. So in binary, then you would have reading up. You'd have 1 0 0 1 0 0 1 0 1 1 base 2. Okay. A little bit longer.
Which one would that be?
You would start here and go that way.
So why do all these? Wait, hold on. I have a question. I just figure out.
Okay. Right. Well, while you're thinking about it, I'm going to go talk about how we do decimals, because this is how you do the whole number part. I also want to talk about how we do decimal part. Okay. Same kind of idea. So if we do the decimal part.
I figured it out.
Oh, you figured it out? Okay. All right. So let's say we had a decimal part that we wanted to do. So let's say we had, I don't know, 0.487. I don't know. Probably got to repeat. That doesn't matter. Okay. So same idea here. This 4 is the 10th place, correct? So this is 4 times 10 to the negative 1. That's 8 times 10 to the negative 2. 7 times 10 to the negative 3, and so on, correct? If we're going to change it to a different base, we want each of those places to represent b to the negative 1, b to the negative 2, b to the negative 3, and so on. All right? Okay. So this would be, if we want to change it, again, I would need an a0, b to the negative 1, a1, b to the negative 2, or I'll call it, let me call it a1 instead of a0. a1, a2, b to the negative 2, a3, b to the negative 3, and so on down the line, right? Yeah? So again, just like what we did when we were converting the whole number part, I want to try to get a handle on each of these digits as we go. Well, let's first focus on how we can get the a1. If I want to get the a1 all by itself, what would I need to do? Yeah, multiply by b, right? That'll get the a1 by itself. So you would take this 0.487, whatever that happens to be, times the b. That'll be a1 plus a2b to the negative 1, a3b to the negative 2, and so on up the line, right? We agree with that? Okay. So notice that whatever this number is here, well, the A1 part better be a whole number, right? Right, I want a whole number times b to the negative 1, not a decimal part, right? This part probably still has decimals, depending on what we're multiplying by. We can figure out the whole number part by subtracting off the decimal part, right? The integer part, again, will be what we need. And then what's left over, we do the same process again, okay? So we multiply by the base. The whole number part is what's going to give us the A1, right? What's left over in the decimal part is we'll do the same process again. Multiply by b, take the whole number part for A2, subtract off the whole number part, have a decimal part, do it again. Just keep going until either it stops, it terminates. It's also possible these will repeat. Okay, so just see what the repeating pattern is. Okay. So let's see if we can put that into Excel real quick. All right. I already have the base over here. Let's change it back over to base 6 because that was what we started with. Let's say now I want to convert that 0.487 or whatever the heck. I wrote 487, didn't I? Okay. All right. That's the number I'm going to convert to decimal. Not decimal, to base 6 places for below the radix point. All right, so the first thing I'm going to do is I'm going to take that number and I'm going to multiply it by the base, which is back over here in A1. Again, I don't want the base to change, so I'm going to put dollar signs on the A1. The A and the 1, because again, when I copy this, I don't want that to change. Okay. This should leave some sort of a decimal. Whoops. We did, all right? Okay. The integer part is the part that we want for the digit, correct? Okay. So here, to get the integer part, I'll just take integer of that number here. Okay. Now again, this is going to be the one, this is going to be the digit that's closest to your radix point, right? Okay, because we've only multiplied by the base one time. Now, going forward, I want to do the next decimal part. So here, how would I get the 0.922? How can I get the 0.922 out of it? That's the part that I want that's left over. Yeah, just subtract, well, yeah, we can take this G1 and subtract H1, right? That'll leave the decimal part. We agree? And now I should be able to just copy those two cells down. Ooh, no, it didn't. Oh, I did lose my dollar signs. How did that happen? Oh, I know why. I hit the arrow key to go to the next one, and it just moved the whole cell because I was still in there. Sorry about that. Thank you for telling me that. That was weird. Okay, there we go. Copy those down. That should look like that. And now grab all three and pull. Yeah, it probably won't terminate. Yeah. How did I get what? I'm sorry. Which part? I'm sorry. That?
Yeah.
Oh, I just took these two and copied.
Stop doing it once you get down to that cell 13. Oh, so it was base 6.
Oh, you want to do, so this is the, oh yeah, the integer part will just be that. So we want, I just want the integer part of this piece, not the division. So I just want integer of that, all that stuff. Okay. Whoops, I mistyped it. I put an extra symbol. There we go. Yep. Yeah, it'll take a while before it starts repeating, but eventually it should repeat. H2. I just copied from H1. F2 is G1 minus H1 because I want the decimal. I want what's left over in the decimal part from the previous step. Okay. So yeah, it just keeps going over and over again, right? What's that? Oh, did it terminate at some point? It might have been from rounding error though. Yeah. Notice right here, it looks like we're getting some rounding error issues starting up. Yeah. Oh, at this point, you can highlight just those three cells, starting at the 0.922. No. Just highlight. There you go. Leave it like that and just click and pull across, highlight across. No, not there. Right there. Yep. There you go. And now grab your plus. Now go down to the other part. There you go. And now go down. There you go. You got it. Yep. All right. Yeah, so notice eventually, it's doing enough computation, it's getting some rounding errors here. I mean, it's good enough for what we've got so far, but eventually it gets some rounding errors. Again, we'll be interested in changing things to base 2, so I can put a 2 in here. And then notice here we've got some zeros and ones for our decimal places. My guess is eventually, if you're doing enough divisions and using these numbers, Excel has some issues built in some places where you can get some interesting decimal parts. So the precision gets off eventually in Excel. I don't know why, but there are some weird little quirks. Anyway, we'll talk more about this next time. In particular, we need to talk about how we're going to store these numbers in the computer. So we'll talk about that next time. Probably do some derivative computations. So you won't be able to do number 2 on this one right now. So then you got to talk about that next time. But everything else we talked about. So. Did I give everybody an extra one? Oh, there's an extra. Did I give an extra one there? You get one, Justin? You only get one? Okay. I put it 19. There's 19 or plus. I don't know why I don't have that. Oh. I didn't know if you had 2 sheets or not. Okay. No, I'm just making sure. I was just. Okay. Sean, I'll email it to you. I don't know why I don't have it. I had it printed off. Oh, I know why. I didn't grab the original off the copy. I'll email it to you right now so you have it. Sorry about that.
We were asking you a question. You said nothing.
I'm so sorry, I didn't say anything back. I saw this, it was late for the recommendation for the and that's all I read. So when it did that real quick, they read it, I didn't read the other part. I'm so sorry. Yeah. I feel so bad. Right. Oh, here, this one equals minus. We're just trying to grab the decimal part off. Okay. Yep, that's what we're doing. Then you just need to copy that. It should be able to make that.
Yes,
There. There you go. Yep, there you go. You're welcome.
You said you should sit here.
I'll be distracted.